recording going here. Tony launched the ball or a ball into the air. Let me get my pen out. The height of the ball can be represented by the equation given, where h is the height and t is the time in seconds after the ball is launched. We got to graph the given equation, state the coordinates of the vertex, explain this meaning in the context of the problem. All right, so we need a graph. So let's start with the calculator, because it didn't say algebraically. Now they're using t's here, but we can think of it in terms of y's and x's instead of h's and t's. That's perfectly reasonable. In terms of creating the graph, one thing we're going to have to consider is the domain, a reasonable domain. Like, for example, will negative time make sense? No. What about negative height? Maybe, but it doesn't seem like it would be that way in this case. All right. It depends on what you define as ground level. 0 level, if I say this is height 0, then you could have negative heights. But if this is 0 level, I don't see how you're going to have negative height unless that ball can somehow burrow through the ground. All right. So there is context, or there are certain contexts that allow for negative quantities, but this doesn't seem to be one of those. All right. So as far as my window is concerned, what I'm going to do is I'm going to select 0 for my x min. I honestly have no idea what my x max should be. I don't know how long it's going to take for this object to complete its trip. I could take a look in the table and get a sense, but I could also just take a shot in the dark. So that's what I'm going to do. I'll make it 0 to 10.
Oh, Mr. Ken. How do you get to that window again?
Oh, yeah, window. Right next to y equals. All right, so my display is a little bit different from yours, so you have to scroll down a little bit to find y min. But I'm going to make my y min equal to 0. My y max, well, again, same idea. I don't really know what the maximum y value is going to be. There is some calculator techniques or tricks that will allow us to figure that out, but I don't want to get into that just yet. So I'm going to take a shot in the dark and say 10 also. And then we'll tweak our graph. All right, so I'm going to hit graph. Oh, that's the other thing. My display is different. All right, well, when you hit graph, do you get a complete picture of your parabola? No. You get an error.
Yeah, it says invalid dimension.
Oh, okay, you have a stat plot on. All right, so hit y equals. And then on the top, you'll see one of the plots that's bolded.
Yeah.
Go on to the one that's bolded, hit enter, and then hit graph again.
Yeah, it works.
No, it works? Okay. So do you see both legs of the parabola?
Barely.
Barely? Okay. So, and you definitely don't see the top, right?
No.
Okay. So in your window, we want to make your x max a little bit wider, all right, because you're only seeing one of the legs. Are you seeing the downward leg?
Yes.
You are seeing the downward leg. You're not seeing the upward leg?
I'm seeing a bear.
Let me see what you got. Okay, so actually your horizontal window is good because you're not seeing it on the upswing as much as you are on the downswing, and that's fine because it's already starting off 5 feet above the ground. I'll explain what that means in a second. What we're not getting is the height. We're not getting the top point. So for y max, make it something like, well, something bigger than 10. So try a number. So try a number bigger than 10, like 20, and then hit graph again, and see if you get the turning point on the top end of the parabola. No? Okay, so then do it again. Now try 30, 40, or 50, something like that. Thanks. Do you have a complete parabola now? Yes? What was the y max that did it?
60.
60?
Yeah.
So 0 to 10, 0 to 60, hit graph. That should give you a good look at the parabola. All right, I'm going to try to tweak my window so it kind of looks like that. Yeah, if you're getting invalid dimension, that's because you have a stat plot on. So that's what I was telling Tyler. You just go into y equals. On the top row, you'll see plot 1, 2, or 3. It'll be bolded. Hit enter on the one that's bolded, and then hit graph again. So my stat students use these calculators also. If you borrow mine. That's X scale. You can just leave that at 1.
I don't see a full.
Mine doesn't even show anything. It just keeps moving around like a thing.
Yeah, mine's the same.
Oh, you don't have the power of 2, right?
Oh, yeah.
I'm for adding.
Alright. So what you done with this? How do you break that? Like what do we do before?
What I do is just zoom 6. If folks, that's a good question. If you want to get your calculator back to your normal -10 to 10, just hit zoom 6. That's your standard zoom. That'll reset it back to ordinary settings. But for now, we want it like this. So. Oh yeah, once you click, you have to have a number in there in order to get out. All right, so we have a good looking parabola here, but I mean, it's great that it's a good looking parabola on our screens. We need it to be a good looking parabola on paper. All right, so what I want is a window that shows me the parabola, which we have. And based on my scale here, it's a little easier to see on mine, but we know generally from 0 to 60, 0 to 6 will get the job done, right? So that gives you a clue as to how you should scale your graph. When you're coming up with the actual plot on paper, we want to have a reasonable scale for our graph. So horizontally, I'm not worried. I can go by ones and I'll be perfectly fine. But vertically, I'm not going to be able to go by ones and get up to 60, right? So I want to go with a nice factor of 60 that'll get me to 60. So what's a nice factor of 60? Factor is a number that divides evenly into another number. 10. Yeah, 6 works too, but then we'd have to count by 6s. Which would you rather do? Count by 6s, count by 10s? You know, so you know, it's a matter of preference. If your answer is I'd rather count by 6s, then that's great. A lot of this is going to be estimation anyway. So if you say, I'm going to count by 2s, I'm going to count by 3s, by 6s, by 4s, whatever fits, that's perfectly fine. You want to count by 3.7s, I don't care. As long as it fits, and as long as you plot your points as accurately as you can. All right? If you're only going by ones, you don't have to label the tick marks. But sometimes people do just so that they don't have to count them every single time. So I'm just going to do it. Now, we need a table, and that table has to include the vertex, not because the question's asking for the vertex, but because an appropriately graphed parabola must include the vertex. All right? So I'll go into my table, second graph. We hunt around for symmetry, but we kind of had a sense that it was symmetrical in the 3 to 4 interval, right? So looking at my table here, around 0, a little bit higher, I see that I start getting a little bit of symmetry, but I also get the fact that my turning point is somewhere between 2 and 3 for X, and somewhere a little bit north of 53 for Y. All right, so we are going to have to do a little side work to figure that out. But that side work does not have to be completing the square, all right? But what I can do, just at least to get this ball rolling, is I can plot these points. 0, 5 is easy enough. 137, again, ballparking it. 2, 53, right about here. 3, also 53, and we're using symmetry to bring it back. So wherever you ballpark the height at 1, you want to ballpark it the same way for 4. Same idea for 2 and 3. All right. 5 is back at 5. Then we're going to hit the ground somewhere between 5 and 6. This question does not seem to be asking about, yeah, it doesn't ask about the roots, so I'm not overly concerned about that. And I can get an idea of what the parabola would look like just by tracing it out with what I have. But again, I want to get that vertex, right? So whether you like it or not, this is a technique that you can use in order to find the vertex, and it's the F max. So if you go into the math menu, there's an option that says F max. We talked about this before. Now, this is in lieu of doing it algebraically, because that formula x equals negative b over 2a for the axis of symmetry is a wonderful formula. But you're still doing stuff by hand. If you want to avoid doing things by hand, then you want to, make it your business to become more and more comfortable with the calculator. Right? So F max is going to give us the axis of symmetry. It's going to give us the x value for which the function has a maximum. You just got to know the language, right? So I select F max in my home screen. Then I type in the name of the function, which is y1. And again, we get that in the alpha trace menu. We tell the calculator what the variable is in the function. Later on, even in this course, we'll see situations where we're going to put expressions in that have more than one variable. Well, actually, more than one letter, but only one of them is a variable. I've actually already done that a little bit, but we're going to formally address that. Then an interval for which the calculator should look to identify where that function has a maximum. All right. So for that, this ties in a little bit better than the last time we did it, because you have a living, breathing graph, really. I put an example of how this really works right on paper, because really I'm just looking at these particular x values. I mean, there are t values here, but I'm just looking at these particular values. I want to be staying in this interval, right? So whatever I selected to use to label my graph here, or even you could even think of it as my x min and x max in my window. Whatever I selected for that is what I should put in now. All right. So that should be 1 comma. In this, I'm going to use 6. But you could say 1 comma 10, or 0 comma 10, because that's what you put in for your domain. All right. But again, alpha trace y1 comma x comma, I'm using 1 and 6 because I know the x value that leads to my maximum is definitely between those two numbers. All right, then I hit enter. Now the calculator again is a little iffy with how it rounds, but it's saying 2.5. All right, so this is equal to 2.5. All right, so my axis of symmetry, x equals 2.5. All right, so that's avoiding the process, or any formulas really. I mean, but the trade-off is you're memorizing one thing to avoid memorizing something else. So that might be a wash. One thing you definitely don't have to do is completing the square, right? And completing the square, I mean, it has its place, but from your perspective, that place only seems to be when a question asks you to do it by completing the square, right? So that's that. And then the next step, this. It's been up here all year, all right? I know on that side it's a little hard to see, but to find y given an x value, type your equation in y1, we already did that. Select alpha trace y1 and then type in the x value and hit enter, all right? So alpha trace y1, put in your 2.5 and hit enter. That's a quick and easy way to evaluate a function. So that gives you your vertex is 2.5, comma 55. All right. The more comfortable you become with doing something like this, first off, the less you actually have to work to memorize it. It becomes more intuitive. And then also, it just takes less time. You start realizing you're doing it super quickly and you're not even really putting any effort into it. Right? Think in terms of multiple choice questions on a test. Okay? So any question that asks you to find the vertex on a multiple choice question, none of this is really anything that I should have had to write down. I'm only writing it down so that you have notes. But on a test, for a multiple choice question, all of this is happening behind the scenes. So I would have come up with the axis of symmetry, vertex, pretty much, I mean, I could even get the roots, all without having to put pencil to paper except for the answer, right? So I can plot 2 comma 55 as soon as I remember where I put my pen. 2.5 comma 55 is going to be about right here. Which, if you were to estimate it anyway, is where you would have put the point, but it's nice to have some precision. I'm going to make it a little thicker. Not that it's getting any better. Let me try it this way. I'm going to make it like Shrinky Dink style. Maybe it'll look better if I zoom out. All right, so we got the coordinates of the vertex. Now we need to state what it means in the context of the problem. All right, that's actually pretty easy, as long as you take note of what the units are. When it comes to word problems, the units are really everything. All right, h is the height, t is the time, and I made this like super ginormous. Now I'm regretting it. Not much better, but I'll take it. All right, so this is time versus height. So in the context of the problem, we could say that after 2.5 seconds, the ball has reached a height of 55 feet. So all we're doing is we're incorporating the units into the explanation, and it really covers everything we need. So after 2.5 seconds, the ball has reached a height of 55 feet. I think it was feet. Yeah. All right. Does this graph depict the actual trajectory of the ball? Explain. Well, I suppose it kind of depends on what the word trajectory means. Does anybody know what that word means?
Like a trail of, or path of something moving?
Yeah, exactly. Couldn't have said it better myself. Trail or path of something moving. All right. So the big question would be, is this the trail or path of the ball moving? Well, the short answer is maybe, maybe not, right? But this is a representative of time. So a horizontal distance would not be measured in seconds, right? So if this were actually a path, then this horizontal axis should be in terms of feet also, just like or some sort of linear measure, just like the height is, but it's not, it's in terms of seconds, right? So, because the reality is they didn't tell us the angle at which this ball is launched into the air. It could be launched straight up and down. It could be thrown kind of at I was going to say sideways, but what I really mean is at an extremely low angle, so more of a line drive with a little bit of a loft. as opposed to like airing it out. You know, so there's a lot of different possibilities here. There's no guarantee that the ball would necessarily have to follow this particular path if it's launched in the air, right? So, but the short answer, the quick and easy answer is no, because a path should compare. I can't even write anymore. Horizontal and vertical distances traveled. I mean, really, if you just asked, like, how far has the plane traveled? You know, if a person answered 30,000 feet, you'd be like, okay, you're talking vertically. 2,000 miles, okay, horizontally. How far has the plane traveled? 2 hours. Okay, but what does that tell you? Like in terms of a distance, if you don't know how fast it's going, then, you know, that could be Chicago, or it could be like Jersey. I don't know. Depends on the size of the plane, I guess. But the distances tell a better story. That's really what I'm getting at. All right. So again, aside from my choppy handwriting, no, because a path should compare horizontal and vertical distances traveled. Oh, and the even worse one. After 2.5 seconds, the ball has reached a height of 55 feet. So let's hop on to number 3 on the next page, because this one talks about routes as opposed to the previous one, which talks about the maximum height specifically. So, quadratic function models the height of a volleyball in feet after X seconds. Algebraically determine how long the volleyball is in the air. But what I'm going to do is draw a very quick sketch. So, volleyball is in the air for some unknown amount of time. I'm going to draw a horizontal, vertical axis, poor quality, of course. It's in the air. In order to determine how long something is in the air, what we would want to do is determine how long it took to get from the start to the finish. All right, because this horizontal axis is time. All right. The reason I drew it this way is because, I mean, it said volleyball. I can't make the assumption that it's starting on ground level. I mean, I suppose if the player laid out to try to what was it called? Bump? I think it's a bump, right? Is it even still a bump when you lay out like, yeah, it's still a bump, right? Yeah, so like just kind of went horizontal, like on the ground, and bumps it at the last second, right before it hits the ground. That would be the only instance that I can think of that would allow for the ball to essentially start at ground level. But most other times it's starting a little bit above the ground. Now it could end up on the ground level, right? That's the whole objective, right? So we can't make the assumption it's starting on the ground level, which means that we're not looking for the vertex here, because that's not going to tell us how long the object is in the air. That's just going to tell us how high it's going, right? If we find the roots, that'll tell us how long it's in the air, all right? So we have f of x is equal to negative 16 x squared plus 80x. All right, so we want to find this solution algebraically. First thing I'm going to do is I'm just going to get rid of that f of x and make it a y. All right, so there's easy algebra and then there's difficult algebra. And it varies from person to person because some people find factoring to be the most difficult form of algebra and completing the square not too bad because it's procedural. And most people, I would say, find it to be the other way around. I would recommend that you at least try to factor it first because it'll be a quicker process. And it is an algebraic approach. The reason I say that in this case is because I see, and again, it's through experience, but I see immediately that there's a GCF. All right? If I'm going to find the roots, I want to set my quadratic equal to 0, but I want to use a technique like completing the square or factoring. All right? The one thing I don't want to use is quadratic formula because that's a numerical approach, not an algebraic approach. All right? So I see I have a common x here. And really, GCF is ideal. I'll settle for a CF. Right? Because just a common factor gets the job done when solving equations. Greatest common factor makes life a little bit easier, but let's say you don't recognize that a negative 16 could also be factored out, so let's just pull out the x. In which case you'll have negative 16x plus 80. In either event, you're looking at two equations that are going to be very easy to solve. X equals 0, negative 16x plus 80 equals 0. So the x equals 0 is already solved, right? And actually this is telling me that the volleyball did start off at ground level, but I couldn't make that assumption going in. Right? I didn't want to take that chance. All right? I want to solve this second equation by subtracting 80 from both sides. I'm looking at negative 16x equal to negative 80. Divide out the negative 16. And what do I get? 5. All right. So this was my suspicion or assumption. All right. But in actuality, I'm looking, that's not what should have happened there. It looked more like this, going from 0 to 5 in terms of time. So how long was this volleyball in the air? 5 seconds. So therefore, 5 seconds. Now, the one thing you got to be careful about is it's not 5 seconds because this x value was 5. It's 5 seconds because the difference between the two roots is equal to 5. All right, so if you think that's something you're probably going to forget or not think about, make a little note, simple note, just say 5 minus 0. And you could say end, start, assuming your pen wants to work. And it'll be a good reminder when you're looking this over as to why we made that final conclusion. All right. So I definitely talked longer than I wanted to, but these are two exemplar problems, two very important types of problems that you're going to spend some time fleshing out over the next couple of days. And so really what you want to do is make sure that you understand these two problems because these are your two model problems to answer everything that follows. Because if you look at the next one, algebraically determine and state the vertex. Interpret the meaning of the vertex. Number of seconds to reach the maximum height, so vertex again. All right. State the time interval in seconds during which the height of the object decreases. So once you have the vertex, it's starting to go downhill. So these two skills are going to come into play big time, in conjunction with the stuff that we've been working on.